A black body is one which completely absorbs radiation of all wavelengths incident on it. The radiation emitted by such a body are called blackbody radiations or full radiations. The energy emitted from a black body depends only on frequency nu and temperature T of the body. In thermal equilibrium, the emissive power of the black body for different wavelengths are measured by means of an infrared spectrometer and a bolometer. The observed spectrum of radiation emitted from a black body at a particular temperature is shown here. This curve shows that the energy is not uniformly distributed and the intensity of radiation is maximum at a particular wavelength. Using classical concepts that a blackbody radiator emits radiation of continuously varying wavelengths from 0 to infinity, Rayleigh and Jeans derived an expression for the radiated energy per unit volume, energy density, E, in the wavelength range lambda and lambda plus d lambda, as E times d lambda equals 8 pi divided by lambda to the power 4 multiplied by k d lambda. The radiated energy per unit volume in the Rayleigh-Jeans expression becomes 0 at very long wavelengths. As wavelength tends to infinity, frequency tends to 0, as observed experimentally. However, this equation says that the emitted energy increases rapidly as lambda decreases and approaches infinity for very short wavelengths, which is in complete disagreement with experiment. Wien also attempted to explain the observed spectral density versus frequency curves. Based on thermodynamic arguments, he derived the expression as E times d lambda equals 8 pi times hc divided by lambda to the power 4 multiplied by e to the power minus hc over lambda times k times t into d lambda, which explains experimental curves at high frequency but fails at low frequency regions. Thus, the energy distribution of a black body could not be explained on the basis of classical theory. This difficulty was resolved by Planck by treating the problem on the basis of entirely different concept, which discarded the classical idea of continuous exchange of energy between radiation and matter and replaces it by the new idea of discrete exchange of energy between radiation and matter. For explaining the distribution of energy in the spectrum of a black body, Max Planck in 1901 put forward quantum theory of heat radiation. According to this theory, a black body radiation chamber can be supposed to be filled up with some simple harmonic oscillators, known as Planck's oscillators, and each has a characteristic frequency of oscillations. Planck proposed that energy of such oscillators cannot change continuously but is limited to a discrete set of values, such as integral multiple of some small unit of energy, E, called the quantum of radiation. And this quantum of radiation is called a photon. Thus, according to this hypothesis, each photon has an energy proportional to the frequency nu of oscillator, that is, E equals h times nu, where h is the universal Planck's constant. Its value is equal to 6.62 times 10 to the minus 34 joule-second. In other words, Planck's quantum hypothesis is consisted of the assumption that the radiation oscillators are not excited to a continuum of energy states, but that these oscillators exchange energy with the surrounding in discrete units, h nu, so that only available energy states of excitation are given by E equals n times h nu, where n is called the quantum number, can be 0, 1, 2, 3 and so on. On the basis of this hypothesis, one can show that expression for the energy density E in the range d lambda has the following form. E times d lambda equals 8 pi hc divided by lambda to the power of 5 multiplied by a term changed by Max Planck. This is Planck's radiation law in terms of wavelength at a given temperature. This formula fits the experimental curves very well for the entire wavelength range. Further, the classical expressions, the Wien's law and Rayleigh-Jean's law, can also be deduced from it as particular cases. Planck's quantum theory was able to interpret fully and different characteristics of blackbody radiation, which classical theory could not. The essential feature of the theory is that radiations are emitted and absorbed not continuously but in discrete units, one at a time, and the energy in each unit being given by h times nu, called quantum or photon. The Planck hypothesis, which was originally proposed to explain the observed spectrum of a blackbody, later on applied to explain a number of other phenomena which could not be explained by classical theory. These phenomena, for example, are photoelectric effect, Compton effect, specific heats of solids and gases, spectrum of hydrogen atom, and photochemical reactions, etc. Thank you very much for listening. See you in the next chapter. Thank you very much for watching the video. If you want some more videos like this, please like, share and subscribe to my channel. Till then, take care, bye bye, stay home, stay safe.